Students, in this video we will study about IGBT or insulated gate bipolar transistor, and it is something of a cross between a conventional BJT and a FET, or you can say MOSFET, making it ideal as a semiconductor switching device. Now in this video we will study about the symbol of IGBT, its advantages, its structure, its working principle, then its transfer characteristics and the output characteristics. Now to begin with, this is the symbol of IGBT, where we have the three terminals, the gate, collector and the emitter. The symbol combines that of a MOSFET and a BJT. Now the IGBT transistor takes the best parts of these two types of common transistors, the high input impedance and high switching speeds of a MOSFET with the low saturation voltage of a BJT, and combines them together to produce another type of transistor switching device that is capable of handling large control emitter currents with virtually zero gate current drive. It combines both the advantages of BJT as well as MOSFET. The insulated gate bipolar transistor IGBT combines the insulated gate, which is the first part of the name, the insulated gate technology of the MOSFET, which is the first part, that is the insulated gate portion of the name IGBT, with the output performance characteristics of a conventional bipolar transistor, which justifies the second part of its name. The result of this hybrid combination is the IGBT transistor, which has the output switching and conduction characteristics of a bipolar transistor, but is a voltage control device like a MOSFET. Now, before we move to the structure of IGBT, let me tell you these IGBTs are mainly used in industrial electronics, or you can say power electronics applications such as inverters, converters and power supplies, where the demand of solid state switching device are not fully met by power bipolars or power MOSFETs. High current and high voltage bipolars are available, but their switching speeds are low, while power MOSFETs may have higher switching speeds, but high voltage and high current devices are expensive and hard to achieve. So we move to IGBT, which combines both the characteristics of MOSFET as well as BJT. Now, the structure of a IGBT. Now, IGBT has three terminals attached to the three different metal layers. The metal layers of the gate terminal is insulated from the semiconductors by a layer of SiO2, a silicon dioxide layer, which insulates the gate terminal from the semiconductor layers beneath. Now, IGBT is constructed with 4 layers of semiconductors sandwiched together. This you can see in the diagram. The layer closer to the collector is the P plus substrate layer. Above that is the N negative layer. Another P layer is kept closer to the emitter and inside the P layer. Then we have the N positive layer. The junction between the P positive layer and the N negative layer is called the junction J1, and the junction between the N negative layer and the P negative layer is called the junction J2. Now, to understand the working of the IGBT, consider a voltage source VG or VGE connected positively to the gate terminal with respect to the emitter. Now, consider another voltage VCC connected across the emitter and the collector, where collector is kept positive with respect to the emitter. See, here between P and N negative layer, they have mentioned in the diagram, they have mentioned between P and N negative layer is J1 junction, and between N negative and P negative layer it is J2 junction. Now, again we are saying we have to consider a voltage source VCC connected across the emitter and the collector, where the collector is kept positive with respect to the emitter. If this is the case, then the junction J1 will be reverse biased, whereas the junction J2 will be forward biased. Since J2 is in forward bias and J1 is in reverse bias, there will not be any current flowing inside the IGBT, that is from collector to emitter, due to the reverse bias of junction J1. Initially, considering that there is no voltage applied to the gate terminal, at this stage the IGBT will be in a non-conductive state. Now, if we increase the applied gate voltage, due to the capacitance effect of the silicon dioxide layer, the negative ions will get accumulated on the upper side of the layer and the positive ions will get accumulated on the lower side of the silicon dioxide layer. This will cause the insertion of negative charge carriers in the P region. Higher the applied voltage VG, greater the insertion of negatively charged carriers. This will lead to a formation of channel between the J1 junction, which allows the flow of current from collector to emitter. The flow of current is represented as the current path in the diagram. When the applied voltage VG increases, the amount of current flow from the collector to the emitter also increases. Again, I am saying this J1 will be reverse biased, J2 will be forward biased. Because of J1 being reverse biased, we will not have any flow of current when there is no VG or VGE. But when we keep on increasing VGE, due to the capacitance effect, there will be negative charges accumulated within the P layer of J1 junction, and the current will start flowing as we go on increasing VG. The increase in the negative ions or the formation of channel will increase and current will start flowing between the collector and the emitter, that is from collector to emitter, because electrons are flowing from emitter to collector. So current flow will be from collector to emitter. Now we can also see the working principle of IGBT as a circuit. Herein we see the IGBT, the symbol of IGBT here, they are biased with the VG current at the gate, which will provide the current IG, and the input voltage VGE, and the output voltage flows across the resistance R, which is the IC, and the output voltage is VCE. So as we go on increasing VG, IG will increase, and which will further increase our VGE. And Vg, this increase in Vg will again help in increasing IC, and there will be a drop in VCE. Now this is the transfer characteristics of an IGBT. Now here we see, as it is a transfer characteristics, we have to plot the output current versus the input voltage Vg. Now as we all know, as there is a very less or zero Vg, there will be very minimum flow of current, because the capacitive layer or the channel has not been formed yet. But as we go on increasing Vg, after a certain point a perfect channel will be formed, and there will be flow of electrons from emitter to collector, and there will be flow of current likewise from collector to emitter, and we see a sharp increase in IC after a threshold voltage which is almost equal to 1 volt for silicon. Now this is the output characteristics of IGBT, wherein we can see this is almost similar to the output characteristics of a BJT. Now when there is, here we plot the two output we plot output current across output voltage at constant Vg. When Vg is 0, there is a very minimum flow of current due to the minority carriers, which is our cutoff region. But as we go on increasing Vc, our IC keeps on increasing and saturates at a certain point, which will then go to breakdown. So this is all about. Here we see that Vg4 is greater than Vg3, is greater than Vg2, greater than Vg1. So this is all about IGBT. Now the main advantages of using the IGBT over other types of transistor device are its high voltage capability, low on resistance, ease of drive, relatively fast switching speeds, and zero gate drive current, which makes it a good choice for moderate speed, high voltage applications such as in PWM, variable speed control, SMPS, or solar power DC-AC inverters and frequency converters. So this is where we can end the video today.